Imagine standing under a clear night sky, gazing at the heavens, and witnessing a celestial spectacle unlike anything you've ever seen. Amper's brilliant streak of light, a glowing tail stretching across the darkness, and the sudden realization that you are observing something ancient, perhaps a fragment of the solar system's earliest days, or even a traveler from another star system. This is the story of two remarkable comets, C2025 R2 SWAN, a long-period comet with a 1400-year orbit, and 3I Atlas, an interstellar visitor making its one-time passage through our solar system. While they differ in their origins and destinies, both offer profound insights into the vast dynamic universe we inhabit. Comets have always captivated human imagination. They are cosmic wanderers, born in the distant reaches of the solar system or beyond, and they arrive in the inner solar system only rarely, often carrying secrets from the past. Some, like C2025 R2, are members of our own solar system, their elliptical orbits bringing them close to the Sun before sending them back into the cold void. Others, like 3I Atlas, originate from interstellar space, arriving in the solar system with no intention of returning. Their brief appearances are fleeting, but the knowledge they provide is invaluable. Each comet tells a story of the forces that shape the solar system, of the materials that form the planets, and of the mysteries still waiting to be uncovered. C2025 R2 SWAN was first detected in images captured by the Solar and Heliospheric Observatory, SWAN's SWAN instrument, revealing a glowing object with a tail stretching across the sky. Its discovery marked the beginning of a dramatic journey. It reached perihelion, the closest point to the Sun, just days after its detection, and its fate remained uncertain as it faced the intense heat of the solar environment. Meanwhile, 3I Atlas made headlines as the third confirmed interstellar object to pass through our solar system, following in the footsteps of 1I Oumuamua and 2I Borisov. Unlike C2025 R2, 3I Atlas is not bound to the Sun by gravity. It arrived from interstellar space, its trajectory shaped by the motion of the Milky Way, and it will soon depart, never to return. But what do these comets truly represent? Are they simply passing spectacles? Or do they hold deeper significance? The answer lies in the science behind their movements and compositions. C2025 R2's long orbital period suggests that it may have originated in the outer reaches of the solar system. Perhaps the Oort cloud, a vast spherical shell of icy bodies that marks the solar system's boundary. Its eventual return in 1400 years, if the current estimates hold, means that future generations will witness the same celestial event we see today. In contrast, 3I Atlas's hyperbolic trajectory indicates that it is not bound to the Sun at all, and its origin lies in another star system, possibly one that predates our own. As we delve deeper into the lives of these two comets, we will uncover the forces that govern their paths, the science that helps us track their journeys, and the questions they raise about the nature of our universe. Are we witnessing the death of a solar system comet as C2025 R2 disintegrates under the Sun's glare? Is 3I Atlas merely a transient visitor? Or does its arrival signify something more profound about the connections between stars and planetary systems? In the following sections, we will explore these questions and more, unraveling the cosmic drama unfolding in our skies. To truly grasp the significance of C2025 R2 SWAN and 3I Atlas, we must first understand the fundamental principles that govern their existence. Comets are not just wandering fireballs, they are remnants of the solar system's formation, composed of ice, dust, and rocky material that have remained largely unchanged for billions of years. Their behavior is dictated by the laws of physics, particularly gravity and orbital mechanics, which determine their paths through the solar system. However, not all comets follow the same rules. Some, like C2025 R2, are bound to the Sun by gravitational forces, tracing elliptical orbits that bring them back periodically. Others, such as 3I Atlas, are interlopers from interstellar space, following hyperbolic trajectories that ensure they will never return. C2025 R2 SWAN is classified as a long-period comet, meaning it takes thousands of years to complete a single orbit around the Sun. Such comets typically originate in the Oort cloud, a distant spherical shell of icy bodies that extends up to tens of thousands of astronomical units (AU) from the Sun. Occasionally, gravitational disturbances from passing stars or the galactic tide perturb these objects, sending them on a slow inward journey toward the inner solar system. Once disturbed, they may take thousands of years to reach perihelion, the point in their orbit where they come closest to the Sun before being flung back into the depths of space. The discovery of C2025 R2 occurred on 11 September 2025, when amateur astronomer Vladimir Bezugli identified it in images captured by the Solar and Heliospheric Observatory's SWAN instrument. This instrument is designed to detect hydrogen atoms in the solar wind, but it is also sensitive to comets, especially those with large diffuse halos of gas and dust. C2025 R2 was first observed at an apparent magnitude of 7.4, with a tail stretching approximately 2 degrees across the sky. Its rapid brightening in the weeks leading up to its discovery, rising from magnitude 11 to 8, indicated that it was undergoing significant activity, likely due to the sublimation of volatile ices as it neared the Sun. By the time it was officially discovered, C2025 R2 had already passed perihelion on 12 September 2025 at a distance of 0.5 AU, 75 million kilometers from the Sun, slightly farther than the orbit of Mercury. Despite its brief moment in the spotlight, the comet's future remains uncertain. Comets that venture too close to the Sun often experience intense heating, causing them to break apart or disintegrate entirely. In fact, C2025 R2 exhibited signs of structural instability, with its brightness fluctuating unpredictably in the days following its discovery. By 16 September 2025, it had reached a peak apparent magnitude of 6.2, making it potentially visible to the naked eye under dark skies, but its brightness quickly declined thereafter. Observers speculated that the comet may have undergone a partial or complete disintegration, leaving behind a cloud of debris that continued to glow faintly against the backdrop of the night sky. The most critical aspect of C2025 R2's trajectory is its orbital period, which remains a subject of scientific investigation based on the limited observational data available. Estimates vary significantly. The Minor Planet Center calculates an orbital period of approximately 1400 years, suggesting that the comet will return to the inner solar system in the year 325. However, the Jet Propulsion Laboratory (JPL) offers a much longer estimate of 20,000 years, placing its next return far beyond the reach of human civilization. This discrepancy arises from the difficulty in accurately determining the comet's aphelion, its farthest point from the Sun, which is currently constrained by the limited number of observations. If the comet's aphelion is indeed as far as 25 AU, as the Minor Planet Center suggests, then its orbit is relatively compact compared to many other long-period comets. If it exceeds 1000 AU, as JPL posits, then it represents a more extreme example of the vast chaotic population of comets that lurk in the outermost reaches of the solar system. Regardless of its exact orbital period, C2025 R2 serves as a reminder of the immense timescales involved in the solar system's evolution. The fact that we are witnessing this comet's journey now means that it may not return for centuries, or perhaps millennia. It is a cosmic clock ticking at a pace incomprehensible to human lifetimes. Yet its motion is governed by the same fundamental laws of physics that dictate the orbits of planets and asteroids. While C2025 R2 is a member of our solar system, albeit a distant and infrequent one, 3I Atlas is an entirely different kind of celestial traveler. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas in Chile, 3I Atlas immediately stood out due to its hyperbolic trajectory, an orbit that is not bound by the Sun's gravity, and ensures that it will not return after its current passage. This places it in an exclusive category of objects known as interstellar comets, of which only 2 others have been confirmed: 1I Oumuamua 2017 and 2I Borisov 2019. The defining characteristic of 3I Atlas is its high orbital eccentricity, which measures how elongated an object's orbit is. While most comets and planets follow elliptical orbits with eccentricities less than 1, 3I Atlas has an eccentricity of 6.141, making it the most hyperbolic interstellar object observed to date. This means that its path through the solar system is almost a straight line, deviating only slightly due to the Sun's gravitational influence. When it entered the solar system, 3I Atlas was moving at a speed of 58 kilometers per second, 36 miles per second, relative to the Sun, faster than any other known interstellar object. This hyperbolic excess velocity, or VM, is the speed at which an object escapes the gravitational pull of a system, ensuring that 3I Atlas will never return. The origin of 3I Atlas is equally fascinating. By tracing its trajectory backward, astronomers determined that it entered the solar system from the direction of the galactic center, near the constellation Sagittarius. More specifically, it appears to have originated from the Milky Way's thick disk, a region populated by some of the oldest stars in the galaxy. This implies that 3I Atlas is not just an ordinary interstellar object. It is among the oldest comets ever observed, with an estimated age of between 3 and 14 billion years. This places it well beyond the age of the solar system, which is approximately 4.6 billion years old, making 3I Atlas a relic from a time when the Milky Way was still in its infancy. Unlike C2025 R2, which will eventually return to the inner solar system, 3I Atlas will soon leave our cosmic neighborhood for good. It reached perihelion on 29 October 2025, coming as close as 1.36 AU, 20-30 million kilometers to the Sun, between the orbits of Earth and Mars. Although it will not come close to Earth, its closest approach to our planet will occur on 19 December 2025, at a distance of 1.8 AU, 269 million kilometers. After this, it will begin its outward journey, eventually passing 0.36 AU, 54 million kilometers from Jupiter on 16 March 2026, before continuing its course into the vast emptiness of interstellar space. One of the most intriguing aspects of 3I Atlas is its chemical composition. Observations conducted by the James Webb Space Telescope and the Very Large Telescope, VLT, have revealed that the comet is unusually rich in carbon dioxide and contains traces of water ice, carbon monoxide, and carbonyl sulfide. Additionally, the detection of cyanide gas and nickel vapor in its coma suggests that it has a unique chemical makeup compared to most solar system comets. These findings raise important questions about the conditions in which 3I Atlas formed and how interstellar comets differ from their solar system counterparts. Perhaps the most profound aspect of 3I Atlas's journey is the insight it provides into the dynamics of interstellar space. The fact that it has traveled across the galaxy for billions of years without being captured by another star system speaks volumes about the gravitational stability of the Milky Way. It also highlights the possibility that other interstellar objects may be passing through the solar system unnoticed, waiting to be discovered by advanced observational tools. When we compare C2025 R2 SWAN and 3I Atlas, the differences in their origins and destinies become starkly evident. C2025 R2 is a member of the solar system, albeit one with a long orbital period, and it will likely return in 1400 years, if not sooner, to grace the skies once more. Its fate, however, is uncertain. Comets that venture too close to the Sun often disintegrate, and C2025 R2 may be nearing the end of its life cycle. In contrast, 3I Atlas is a one-time visitor, destined to leave the solar system forever after its current journey. Its arrival is a rare and fleeting event, a glimpse into the ancient past of another star system. Both comets serve as reminders of the dynamic nature of the cosmos. They are not static objects, but active participants in the grand cosmic dance, shaped by the forces of gravity, time, and chance. Whether it is the slow, cyclical return of a long-period comet, or the swift, one-way journey of an interstellar visitor, each comet tells a unique story, one that continues to unfold as we observe and analyze their paths. As we move forward in our exploration, we will examine the broader implications of these comets, considering what their existence tells us about the evolution of the solar system, the chemistry of interstellar space, and the possibility of other comets yet to be discovered. In the next section, We will delve deeper into the scientific mysteries surrounding these celestial bodies and the questions they raise about our place in the universe. The study of comets like C2025 R2 SWAN and 3I Atlas extends far beyond their immediate celestial paths. These objects are not merely transient visitors in our skies. They are cosmic messengers, carrying with them clues about the origin and evolution of the solar system, the chemical composition of the universe, and the possibility of interstellar exchange. The disintegration of C2025 R2 and the one-time journey of 3I Atlas raise profound scientific questions, prompting researchers to reconsider the nature of comets, their role in planetary formation, and the likelihood of discovering more interstellar objects in the future. C2025 R2's journey presents a compelling case study of cometary evolution and the factors that lead to a comet's ultimate demise. Unlike the more stable short-period comets, which have orbital periods under 200 years and originate from the Kuiper belt, long-period comets like C2025 R2 come from the Oort cloud, a vast reservoir of icy bodies extending up to tens of thousands of AU from the Sun. These comets are only occasionally perturbed by external forces, such as the gravitational influence of passing stars or the galactic tide, and sent on a slow inward spiral toward the inner solar system. Once a long-period comet reaches the inner solar system, it is subjected to intense solar radiation, causing its volatile ices to sublimate and release gas and dust into space. This process forms the coma and tail that make comets so visually striking. However, repeated passages near the Sun can lead to structural instability, ultimately resulting in the comet's disintegration. In the case of C2025 R2, its rapid brightening followed by a sudden decline in visibility suggests that it may have undergone a partial or complete breakup shortly after reaching perihelion. The disintegration of comets is not an uncommon phenomenon. Many long-period comets, such as C1996 B2 Hyakutake and C2006 P1 McNaught, have been observed to break apart as they approach the Sun. The mechanisms behind cometary disintegration are still not fully understood, but scientists believe that thermal stress, rotational instability, and internal pressure buildup from sublimating ices all play a role. In some cases, the nucleus may fracture due to the uneven expansion of volatiles beneath the surface, while in others, the loss of mass from continuous outgassing weakens the structure until it collapses under its own weight. The fate of C2025 R2 raises an important question. Are we witnessing the end of a solar system comet? If the comet has indeed disintegrated, it would mark the final chapter in its 1400-year journey through the solar system. However, if it has only partially broken apart, some of its fragments may continue to travel along its original orbital path, potentially becoming new, smaller comets or even contributing to future meteor showers. The fact that C2025 R2 will return in 1400 years, according to current estimates, suggests that it has not yet completed its entire cycle, and future observations may reveal whether any remnants of the comet survive to make another passage. Beyond the fate of individual comets, the study of disintegrating comets like C2025 R2 provides valuable insights into the structure and composition of cometary nuclei. By analyzing the spectral signatures of the gas and dust released during the breakup, scientists can determine the types of volatiles present in the comet's interior. This, in turn, offers clues about the conditions in the early solar system, as comets are believed to contain primordial material from the time of planetary formation. Moreover, the rate of cometary disintegration is a crucial factor in understanding the long-term stability of the Oort cloud. If many long-period comets disintegrate upon entering the inner solar system, it suggests that the population of comets in the Oort cloud is constantly replenished, perhaps by the gravitational influence of interstellar objects or the galactic tide. This reinforces the idea that the Oort cloud is not a static structure, but a dynamic component of the solar system, continuously reshaped by external forces. If C2025 R2 represents the end of a solar system comet's journey, 3I Atlas symbolizes the beginning of a new chapter in our understanding of interstellar objects. As the third confirmed interstellar object to visit the solar system, 3i Atlas offers a rare opportunity to study the composition and dynamics of objects that originate from outside our solar system. Unlike 1i or Oumuamua, which lacked a visible coma and was initially mistaken for an asteroid, and 2i Borisov, which displayed a more typical cometary appearance, 3i Atlas exhibits a distinctive red-hued coma and an unusual chemical composition, suggesting that it may have formed under different conditions than most solar system comets. One of the most intriguing aspects of 3i Atlas is its origin in the thick disk of the Milky Way, a region populated by old stars with low metallicity, meaning they contain fewer heavy elements compared to younger stars like the Sun. The thick disk is believed to be a remnant of the early Milky Way, and the fact that 3i Atlas hails from this region implies that it may be billions of years old, predating the formation of the solar system itself. This raises fascinating questions about the conditions in which interstellar comets form and whether they share similarities with the primitive building blocks of planetary systems. The chemical analysis of 3i Atlas has also yielded surprising results. Observations by the James Webb Space Telescope (JWST) and the Very Large Telescope (VLT) have revealed that the comet is unusually rich in carbon dioxide and contains traces of water ice, carbon monoxide, carbonyl sulfide, cyanide gas, and nickel vapor. This composition differs from that of most solar system comets, which tend to be richer in ammonia, methanol, and hydrogen cyanide. The presence of nickel vapor is particularly noteworthy, as it suggests that 3i Atlas may have experienced higher internal temperatures than most comets, possibly due to radioactive decay or collisions in its native star system. These findings challenge the assumption that all comets, regardless of their origin, follow the same evolutionary path. If 3i Atlas formed in a different stellar environment, it is possible that its parent star system had a different chemical composition or planetary architecture than our own. This opens up the possibility that interstellar comets could serve as cosmic probes, offering insights into the diversity of planetary systems across the galaxy. Furthermore, the trajectory of 3i Atlas is of great interest to astrophysicists. Unlike the previous two interstellar objects, which were discovered from the northern celestial hemisphere, 3i Atlas originated from the south, in a direction opposite to the solar apex, the point in the sky toward which the Sun is moving relative to nearby stars. This challenges existing models of interstellar object distribution, which predicted that more interstellar objects should come from the northern direction due to the Sun's motion through the galaxy. The fact that 3i Atlas defies these expectations suggests that interstellar comets may be more evenly distributed than previously thought, or that our observational biases have limited our ability to detect them. The age of 3i Atlas is another area of active research. Based on its velocity components and the typical ages of stars in the thick disk, scientists estimate that 3i Atlas is between 3 and 14 billion years old, making it potentially older than the solar system. If this assessment holds, it would mean that the comet has survived for billions of years in interstellar space, enduring the harsh conditions of the galactic environment without being destroyed by supernova explosions, stellar winds, or interstellar collisions. This raises the question, how do comets survive in interstellar space for such extended periods? Do they possess unique structural properties that allow them to withstand the rigors of the galactic medium? Or do they originate from more protected regions of their parent star systems? The implications of these discoveries extend beyond the study of individual comets. If 3i Atlas is representative of a larger population of ancient interstellar comets, it suggests that the Milky Way is teeming with objects that predate the solar system, carrying with them the chemical signatures of long-lost planetary systems. This has profound consequences for astrobiology, as it raises the possibility that organic molecules, prebiotic compounds, or even microbial life could have been transported between star systems via interstellar comets. Additionally, the detection of 3i Atlas highlights the importance of advanced observational technologies in discovering and characterizing interstellar objects. The Vera C. Rubin Observatory, the James Webb Space Telescope, and the Transiting Exoplanet Survey satellite TESS all played key roles in tracking 3i Atlas's journey, demonstrating the power of modern astronomy to uncover fleeting cosmic phenomena As these instruments continue to refine their capabilities, it is likely that more interstellar comets will be discovered, each offering new insights into the nature of the universe. As we look to the future, the study of comets like C2025 R2 and 3I Atlas will continue to evolve, driven by advancements in technology and expanding observational networks. The next generation of telescopes, such as the Large Synoptic Survey Telescope, LSST, and the Euclid Space Telescope, will enable astronomers to detect fainter and more distant comets, potentially uncovering new members of the Oort cloud and more interstellar visitors. Moreover, space missions dedicated to comet sampling and in situ analysis may soon become a reality. While the Rosetta mission provided unprecedented insights into the structure and composition of Comet 67P, Churyumov-Gerasimenko, future missions could target long-period comets or even interstellar comets to study their chemical and physical properties in greater detail. The potential to return samples from these objects would revolutionize our understanding of the early solar system and the processes that led to the formation of planets. Ultimately, the study of comets is not just about understanding these icy wanderers, it is about understanding our place in the cosmos. Whether it is a long-period comet returning after 1400 years, or an interstellar traveler making its first and only visit, each comet carries with it a story that spans millions or even billions of years. By unraveling these stories, we gain not only scientific knowledge, but also a deeper appreciation of the vast interconnected universe in which we live. As we conclude this exploration of C2025 R2 SWAN and 3I Atlas, it becomes clear that these celestial wanderers are more than just distant objects in the night sky. They are messengers from the past, present, and future of the universe. Each comet tells a unique story shaped by the gravitational forces of the solar system, the chemical composition of distant star systems, and the inexorable passage of time. From the slow cyclical return of C2025 R2 to the one-time journey of 3I Atlas, these objects remind us that the cosmos is in constant motion and that our understanding of it is still in its infancy. The discovery and study of these comets have pushed the boundaries of modern astronomy, revealing the complexity and diversity of objects that exist beyond our planetary neighborhood. C2025 R2's potential disintegration underscores the fragile nature of comets, demonstrating how even the most resilient structures in the solar system can be undone by the sheer power of the sun. Meanwhile, 3I Atlas's interstellar origin and unusual chemical composition challenge our assumptions about the uniformity of cometary material, suggesting that the building blocks of planetary systems may vary across the galaxy. These insights not only expand our knowledge of the solar system's formation, but also open new avenues for exploring the origins of life and the distribution of matter in the universe. Yet beyond the science, these comets invite us to consider our place within the vast cosmic tapestry. We are creatures of a single planet, bound by the limits of time and space, yet we find ourselves gazing at objects that have traveled for millennia or billions of years to reach us. The fact that we can observe, analyze, and understand these distant travelers is a testament to the power of human curiosity and the ingenuity of scientific inquiry. Every comet we detect, every spectrum we decode, and every trajectory we trace brings us one step closer to answering the fundamental question: what is our role in the universe? The study of comets is not just about cataloging celestial events. It is about connecting the dots between the past, present, and future. It is about recognizing that the materials that make up our world, the water in our oceans, and the organic molecules that form the basis of life, may have been delivered by comets like C2025 R2 or 3I Atlas. It is about acknowledging that the same forces that shape the solar system continue to shape the evolution of galaxies, the formation of stars, and the distribution of life across the cosmos. As we look to the future of cometary research, we can expect even more groundbreaking discoveries. With the advent of next-generation telescopes and space missions, we will soon be able to observe comets in greater detail, perhaps even sample their surfaces and analyze their interiors. The detection of more interstellar comets like 3I Atlas will provide a window into the chemical diversity of other star systems, helping us piece together the cosmic puzzle of planetary formation. And as we refine our understanding of the Oort cloud and the dynamics of long-period comets, we will gain deeper insights into the structure and evolution of the solar system itself. In the end, the journey of C2025 R2 and 3I Atlas is a journey of discovery, not just for science, but for humanity as a whole. These comets remind us that we are part of something far greater than ourselves, that the same stardust that forged the planets, the stars and the galaxies is also within us. And as we continue to explore the universe, we carry with us the legacy of those who came before us, the curiosity of those who seek to know more, and the hope of those who dream of what lies beyond the stars.